So it says find the limit of 3. Of course, we want to look at 3 from the left and from the right of our graph. So if we look with the graph that we're given, let me use a highlighter here. When we get to 3 from the left, we get there. And when we get to 3 from the right of our graph, we get there. Those are 2 different points. So what can we say about the limit? Does it exist or not? No. If I were to ask you the value of the function at f of 3, what would you say? -1. Right. So remember that your limit doesn't exist there because you're approaching 2 different numbers on the right and on the left. So if you were looking at 2.99 and 2.999 and 2.99999, you would get a different value. You would get closer to 2. Whereas if you were looking at 3.01, 3.001, 3.0001, you would get closer to -1. So that's not a limit, right? A limit is a single term that on both sides you're getting close to. So this does not exist. Let's go to the bottom. The limit as x approaches 3 to the left. That negative sign means to the left. So it just wants to the left. So 3 to the left, the limit is 2. The function does not exist at that point, but the limit does exist if we're just looking at that side. Question? The limit as your function approaches 0 from the right and from the left. So, again, let's take a look. As we approach 0 from the left side, we go there. And as we approach 0 from the right side, we hit that black point. So what about the limit as we approach 0 from the right and the left? They're different. So what does that mean about the limit of 0 as x approaches 0? It doesn't exist, right? Are we clear on this concept? Cool. We talked about how sometimes you can factor stuff out and get rid of a hole in a graph. That's called a removable discontinuity. So, for example, when we were looking at the limit of, or as x approaches 3, without that point, your limit would exist, right? That's called a removable discontinuity. If both of those were open circles, then that would be non-removable, okay? Another renewable discontinuity would be right here. If you just took that single point out, then your limit would exist there. The only time it doesn't exist when you have non-renewable discontinuities is whenever you have a piecewise function where you have 2 open circles, okay? Questions on this? All right, we talked about analytically how to determine the limit of something based on that concept. Lucky for us, most of the time, it's just direct substitution, which means you just plug in the number and you get something out. We know that with a continuous function, like a parabola, as for your limit as x approaches 3, for example, if it's continuous, you just plug it in, you get an output, and that output is your limit of your function. So here, we can plug in 3. We get 3 squared minus 1 over 3 minus 5, that's 8, over -2, which is -4. Okay, no problems there. That's continuous. That's the limit. If I were to graph that and I were to check, okay, let's see, -3.9999, -3.99, -3.9, and then -4.01, -4.001, you would get closer to, 3.01, 3.001, 3.001, and 2.999 and 2.999. you'll get closer to negative 4. Left to the right of 3, because that's what your x is approaching. Is that clear? Okay, this next one, we have some issues if we plug in 5 directly. You can get something like 0 over 0 or a number over 0, and then you can't really find the limit. However, you need to check if it's a removable discontinuity, so you factor and see if you can cross out and remove the hole to see what the limit would be if you were to remove that hole. So we can factor this one pretty easily here. You cancel out what you need to cancel out. X minus 5, that means there's a hole at x equals 5. Okay, that means there's a hole, but it's removable. And now you can plug in 5 to evaluate the limit of your function. It's 5 plus 5 over 5 plus 1. Oops, moving a little too fast. 10 over 6. And then that reduces to 5 over 3. Questions? Yeah. Yeah, from the left side, looking at your function, what is your y value? So this is your graph, this big giant piecewise function. If we're just looking at 3, we have to look at both sides. When we go here, that's 2 different values, so there's no limit just at 3. Because typically to evaluate the limit, you have to look at both sides. So you say, okay, if it's the same number, then it exists. This just says, what is the limit to the left? You just want to look at one side. Forget about the other side. Just to one side, well then it just goes here. Because this is all to the left. If you were looking at the values like 2.99, 2.999, they would get closer and closer to this. The function doesn't exist there, but if we're just looking at the limits, which is what are you getting closer and closer to, what is 2.99 getting closer to, and 2.999 getting closer to, and 2.9999 getting closer to, you would say it's closer and closer to 2. Does that make sense? Okay. Now these are very important concepts because what we're going to do right now is we're going to talk about the point of calculus, and that is finding the slope of a curve. I mentioned this to you before, but you have to understand the idea of a limit, because what we're going to end up doing is something called Newton's quotient, which is awful. When I first learned Newton's quotient and my teacher told me there was an easier way to do it, I was like, why didn't you teach me an easier way from the beginning? It's because it's, again, the conceptual understanding, where things come from first. You do sort of the work and you hate everything, and then I teach you how to do it in 2 seconds. And you're like, okay. So, bear in mind that this first process that I'm going to teach you after I do this last limit question is going to be not fun. All right, so this should say limit. I put log. The limit as x approaches 5, 13. Well, anytime you have a constant, it's just a horizontal line, and the y value for something like y equals 13 is always 13, no matter what your x is, right? So your limit here is just 13. Because if you were to draw this out, you draw a horizontal line on your xy axis, and no matter what your x value is, 5.01, 5.001, 4.99, 4.999, 13, right? Because that's what it means to be a horizontal line. All of these are y equals 13. What's your limit? Y equals x squared minus 25 over x squared minus 4x minus 5. What is your limit? Questions? Do we feel comfortable enough with limits that I can move on to derivatives? Akil, is there anything that you have a question on? concerning the topic of limits?
I'm getting there.
Okay.
Like I'm not completely lost, but I'm getting there.
Do you understand the point of a limit?
Yeah.
Flora, what about you? All right. So, let's move on to this one. I picked one of your homework assignments, or one of your homework questions, for this very reason, because a lot of times in Math SL questions on your exam, they don't actually want you to evaluate limits analytically, just plugging stuff in, right, and canceling stuff out. But what they will do is they'll tell you, okay, well, your limit as your function approaches infinity is this number. And you have to understand that they're giving you a horizontal asymptote. And you have to use that horizontal asymptote to maybe figure out certain values in your rational function, right? So that's why this skill is really, really important. Now, I emphasize here that you really need to remember the characteristics of your e to the x graph, your natural log graph, and your log graph, which I know it's been a long time. But I'll remind you of that when we start looking at derivatives of logarithmic and natural log functions. For now, remember your parent function for your e to the x graph looks something like this. So if I have a -6, what's going to happen to the graph? Shift down. It's a vertical translation, 6 units down. So I'm just going to see what that looks like. Say 6 is somewhere down here. I know from my study of exponential functions that's a horizontal asymptote, right? It's going to get super close, but it's not going to pass that horizontal line. So now they want to know, what is the limit as x approaches, as the x values in that graph get more and more negative? What would be the limit? Yeah, -6, right? What about the limit as your x values get more and more positive? Do you have a limit? Do you approach a value? No. A limit is, what value are you approaching? And if the answer to that is infinity, to say it doesn't exist because it doesn't approach a value, right? It's going on forever. So if given a problem, you were to see this, then that is an asymptote. Okay? Questions? All right. So, let's just read this first part. A rate of change is the change in the dependent variable with respect to the independent variable. This is also called slope. We're going to start real easy. We all remember slope from Algebra 1, change in y over change in x, right? So I'm going to write all these basics down because they're going to matter here in a minute. That's our slope. Okay. We also call that our m value. Now, with distance time graphs, we know that there is a formula that says distance equals rate times time, right? So I'm going to write that down. In other words, if you were to take your distance, which is your y, and divide it by time, which is your x, you would get your rate, right? And in fact, if you were to take the change in your distance over the change in your time, you would get your average rate or your average speed. Does this all make sense so far? Some physics, but all things that I've taught my Algebra 1 class at this point. Now, in Algebra 1, we've dealt with graphs that look like this. You have your distance, and you have your time. Now, what's the problem with the speed here, with the speed component of the constant? But if we're in a car, are we always going to drive the same speed every time? No. What we really have in real life maybe something that looks like that, right? Now, if we're just looking at the line, we just find the slope between 2 points and we find the slope of the graph. But with curves, your slope is different, right? Sometimes it's positive, sometimes it's negative. You speed up when you slow down, right? We need a way to find the instantaneous rate of change. Instantaneous rate of change meaning what? Do you know? Exactly. We need to find a way to find the speed at that exact time. If we can do that, we can find the speed at any time on a curve, right? Because the speed is constantly changing. So I want to find a way to, is there a way for me mathematically to find the speed at a particular instant? And there is, and that's called a derivative. They say the problem in calculating this is that we don't have 2 points as the line only passes through one. This is called a tangent. So anytime we're finding the instantaneous rate of change, for example, maybe I want to find that slope of right there for that point. Right at that point, I want to know the instantaneous rate of change. Well, I need 2 points, typically, to find the slope of the line, right? Well, I only have one. When I draw a line, it only crosses at that point once. Does this all make sense so far? A derivative is the slope of a curve at a tangent line to the curve. Okay. So the derivative, let me say that again. Okay, messed it up the first time. The derivative is the slope of the tangent line to the curve at a particular point. Okay, the derivative is the slope of the tangent line to the curve at a particular point, which we call the instantaneous rate of change. For the people who are gone. So, my task here is to find the instantaneous rate of change at x. X is some time on my curve, if it's a distance time curve or time distance curve. The problem is I don't know how to use calculus to find the slope of the tangent line of that curve. So what I'm going to do is I'm going to find the slope of the secant line that has 2 points that I can just use algebra to find the slope of. If I find the limit as h approaches 0, what I'm doing is I'm saying, okay, let me draw a secant line. Keep drawing secant lines until I get closer and closer and closer and closer to that tangent line where h is so far from x, right? But if I close in on it and I make that h 0, then I'm right at my tangent line. I'm right at the slope of my tangent line. So what we're going to do is we're going to find the limit as h approaches 0 of our slope. Okay? So Let's do that. So, to do that, I'm just going to use my slope formula because I have 2 points, x, f of x, and then x plus h, f of x plus h. You know that change in y over change in x is just y2 minus y1 over x2 minus x1. So y2 minus y1 over x2 minus x1. And you're going to simplify. This is your change in y over change in x. Well, those x's go away. And you get this. That's called a difference quotient in and of itself. That's called a difference quotient. But you don't need to know that term. That's the slope of the secant line. But I want to think of infinitely many secant lines that eventually close the gap between here and here, between x plus h and x. That's a limit. I want to know what value my slope approaches as my h gets closer and closer to 0. Do we get that? Okay, so I need to find the limit as h approaches 0. Sometimes you'll see delta instead of h, but same thing. That's a derivative. When we find that limit, when we close the gap between x plus h and x, as we ask ourselves, what value is my slope as I get closer and closer to my tangent line, you're finding that instantaneous rate of change, which is your derivative. That is called Newton's quotient, and that's what we're going to work with first. So Newton's quotient. Is the limit as h approaches 0 of f of x plus h minus f of x over h. All this is going to end up being is a composition problem. If you understand composition of functions, it's going to take some strong algebra skills and simplification, and then direct substitution with your limit. You'll find your derivative. At this point, it's nothing but algebra, and I'll teach you how to do that. Do we have any questions so far before I talk a little bit about history here? Okay, good. There was actually a huge controversy way back in the day between Sir Isaac Newton and Gottfried Leibniz on who was the true inventor of calculus. You had two guys, one that had just discovered gravity and the apple on his head falling down, that were discovering calculus at the exact same time. Far and away, Isaac Newton is credited for calculus. Leibniz should also be credited for calculus. They went into a court battle, and Leibniz lost rights to claim calculus as his own, which is really sad because they said even here, Gottfried Leibniz was a German mathematician who independently was creating calculus at the same time as Newton. He dared to challenge the great and powerful Newton and was thus shunned by the math community. When he died, apparently no one came to his funeral.
Do you have children?
I don't know. But Newton was a very powerful man. When he published the Principia, it was like as popular as the Bible. Super, super powerful book. So when Leibniz came over here and tried to claim it as his own, they said, no, we're not going to credit you with the idea. However, the ironic thing is, even though we credit Isaac Newton for a lot of the fundamental ideas, and we should because he did come up with the fundamental ideas of calculus, Leibniz is responsible for the notation that we use in calculus today. Without Leibniz, we wouldn't have the notation that actually makes us look at something in calculus and think, okay, I actually understand what this means, what the notation looks like. So let's take a look at some of the terms here. We talked about Newton's quotient. What it calculates is called the instantaneous rate of change. We talked about that. It's called a derivative or the slope of a tangent. The process of calculating this derivative is called differentiation. This last half of the year is all differential calculus. And then next year, we're going to spend about 2 weeks, again, with differential calculus to review. And then we'll go into integral calculus, which is different. Okay? So, important notation here. You're going to see this a lot. When you see the single quote, they want you to find the derivative. They're going to ask you to do the mathematical processes, the calculus, to find the derivative. They want to know the instantaneous rate of change. That's called f prime x. Second notation, super important, which is Leibniz's notation, is dy over dx. You're going to see this a lot as well on your exams. The derivative of y with respect to x. Same idea as change in y over change in x. Okay. Questions? That's all well and good. So let's see the point of this by actually finding the derivative of a curve. You're not going to like me for this process. That's okay. When I teach you how to do this the easy way, you're going to be really upset. Because it's literally like one step. The long way is like 5 or 6 at least. So let's say we want to calculate that instantaneous rate of change for a parabola, the parent function, y equals x squared, when x is equal to -1. We want to find the instantaneous rate of change when x is equal to -1. So we pull out our formula, our Newton's quotient, and we know that that's going to tell us find the limit as x approaches 0 of f of x plus h minus f of x over h. You have to be so careful with your algebra, because you mess up one thing with your algebra, the entire derivative is wrong. So what you do is you say, okay, f of x plus h is x plus h squared, because you're looking at this. You're substituting x plus h in for x, right? You're doing that composition of functions that we talked about in chapter 1. So you're saying, okay, wherever I see x, I'm going to replace it with x plus h. We've done that before, right? So f of x plus h is x plus h squared. F of x is just x squared over h. And we can't forget that we're going to find the limit as h approaches 0. Okay. Now we're going to do some algebra and see what we come up with. So the limit as h approaches 0 of, well, that's x squared plus 2xh plus h squared minus x squared over h. Start crossing stuff off. You get the limit as h approaches 0 of 2xh plus h squared over h. You can factor out an h, so you factor out an h. So you've got the limit as h approaches 0 of h, take that out, 2x plus h over h. Well, your h's cancel out. Gone. So now you're looking at the limit as h approaches 0 of 2x plus h. Okay. Well, how did I find limits yesterday? What'd I do? Substitution. I substitute what in for, I substitute h with 0. Because I'm looking at as h approaches 0. So this limit is just 2x. That's your derivative. Okay, your derivative function. So in other words, your f prime x is equal to 2x. So the instantaneous rate of change asks me, what is f prime of 1? Well, that's just 2. So the slope of the tangent line to a curve at x equals -1. Oh, I'm sorry. Not at x equals 1, at x equals -1. Should be -2, right? The slope of the tangent line to the curve at x equals -1 is -2. That -1 there? The step? So what I did was I said, okay, that is the equation of my derivative. That equation gives me the instantaneous rate of change when I plug in an x value, right? That tangent, equation of the tangent line, because the whole point of the limit was finding that tangent line equation, right? It wants to know particularly, okay, you found the equation of the tangent line, but tell me, what is that tangent line's y value when I plug in x of -1? And when you get -2, that's the instantaneous rate of change. Questions? Any questions on anything we've covered? We were going to move on tomorrow, but actually I think we're going to spend more time with this limit definition of a derivative. Like I said, be very, very careful with your algebra. Especially when it comes to this. We're going to take a look at this tomorrow. What I want you to do today, I originally had a homework assignment for you. You can wait to start that and just work on it in class and ask me questions as you go. But what I'd like you to do now is take some time to figure out number 2 and number 3. Doing exactly what we did here. Be ready tomorrow to discuss the solution because I'm going to walk you through how to do that. Number 2 is okay. Number 3 is extremely difficult if your algebra gets messed up halfway through. Okay? Because you have a fraction. So be careful there. Any questions on anything?
What about the rise and run theory?
Rise over run is slope, which is instantaneous rate of change, which is what we're talking about. Rise over run just tells you on a line how to get from one point to the other. It helps you interpret your slope for a line, okay? But really what we need to understand, and this is a fundamental concept, is slope is the rate of change. That's what slope is. The change in y over your change in x. The whole idea of slope is how's your y changing in relation to x? Okay? That's what the concept of slope is about. Rise over run just says, okay, here's your y-intercept. Rise 3, run 1, and you get the point to make your line. But conceptually, that's not what we're talking about here. We're talking about a conceptual understanding of an idea. All right? That's the important thing with calculus. You have to transition away from the surface level understanding of things like slope as rise over run and start transitioning into slope as a concept, as an idea of instantaneous rate of change. Okay?